So today I'll be talking about garbling gadgets. I will primarily present two results quite orthogonal to each other. So we all know garbled circuits. Garbled circuit is a way to sort of encrypt any circuit such that another party, an evaluator, can evaluate the circuit in its encrypted form and decrypt only to the evaluation of the circuit at the inputs it holds. There was a formalization of a garbling scheme as a cryptographic primitive where you have your function f that is taken as input by the garble algorithm and produces an encrypted form of that called the garbled circuit. And then you send encoded inputs, which can then be used to evaluate into an encrypted output, and then you use the decode to sort of get the output of the function from it. Most garbling schemes, most work in garbling has happened in reducing the size of the garbled circuit because you have to do gate-by-gate encryption, and each gate costs you some amount of ciphertexts. Here is a landscape of garbling schemes till now, and we can see that so this is a number of ciphertexts that you will have to send for each gate in a circuit, which means that the size of the garbled circuit scales with the size of the number of gates. Breaking it down, we have this notion of garbling a gate. Let's just start from there and then see how to build the garbled circuit from there. So let's assume we have a gate G, which takes in inputs wires A and B and has an output wire C. We want to have a parallel notion of a garbled gate for this, where in that case, if you had received the output G of I comma J, then we choose two wire labels here for each wire. Each label denotes the wire taking the value 0 or the value 1. And then, in this case, say AI and BJ. And now, if you have the garbled gate, then you need to be able to obtain the output wire based on the evaluation of the gate on the left-hand side. And now, given that you have a garbled gate, if you can obtain an output label from one of these, then you can sort of continuously evaluate and get a garbled circuit for the entire circuit. Okay, how do we achieve this? This is the classical notion of Yav's garbling, where let's say the evaluator holds one of the 4 possible combinations of wires, which means that one wire for one label for wire A and one label for wire B. Then it needs to obtain this output label given on the right side table. You can simply encrypt these wire labels, output wire labels, by using these evaluation labels, the labels that evaluator holds as key for each row, and then send the encrypted values to the evaluator. And the evaluator can just decrypt one of them because it holds only one of the 4 possible wire labels. An observation here was that if you actually set one of the output labels, because you only have 2 output labels, if you set one of the output labels to just h of A0, B0, then you have a 3 kappa bit ciphertext instead of a 4 kappa bit ciphertext. In the context of circuits, we know that we can represent any Boolean circuit in just XOR and AND gates. And Kolesnikov and Schneider showed a way to sort of use how to garble XOR gates for free, which means that you need no garbled circuit. You can just follow this technique of sampling this secret delta, which is the same for the entire circuit and not revealed to the evaluator at any point. Then you can just set the other label, like the one label, to be the sum of the XOR label and this delta. This way, and when you set your output label for an XOR gate to be the XOR of the 2 input labels, this sort of works out, and the evaluator can do the same on the other end when it obtains the labels. Okay, moving on, we jump to the half gates optimization. Just so you know, we are now at this stage where we had these 3 ciphertexts and one way to sort of compute the output label. What we want to do now is to sort of build towards a linear equation, which we will then use to show that there is a certain restriction of this framework where you cannot actually garble gadgets of higher size. The main idea of an interpretation of the half-gates optimization can be seen as this idea of replacing h of a comma b with h of a XOR h of b. As you can see, this sort of cancels out a few values here, and what you have is this G1 and G2 that you need to send. And an interesting observation here is that the last column, G3, is just the sum of the second and the third column with this additional delta. Right. So does this mean that we don't have to send G3? The problem is the evaluator does not know delta, and you cannot reveal it to the evaluator. So how do they solve it? They say that, well, there are some additional labels that you have, the evaluator has, the garbler has, and if you actually just add the relevant labels to sort of make this equation solvable without revealing delta, then you sort of have an optimized version where you only send 2 kappa bits. And this is what they suggest. I'm sorry for the color there, but you essentially add A0 in the second row and A1 in the fourth row. If you sort of go back to what the evaluator holds in this case, it's actually A0 in the first 2 rows and A1 in the last 2 rows, so this is fine. So, as I said, you can sort of represent whatever we had as a system of linear equations, and you can sort of see this as the thing on the left-hand side, which is something that the garbler has to compute in order to send it to the evaluator, which can then use it to evaluate the gate. This was an observation made in the 3/2 paper, which we will discuss later. But, right, okay. So you have kappa bit labels here, and you derived a 2 kappa bits garble gate. The 3/2 technique introduced by Rozalek and Roy essentially says, how about we slice these labels and use these labels separately? Can we do something better? Again, this is a sort of a reviewed observation. The way they do it is a bit different, but you can sort of see it this way, where you have kappa bit labels, you sort of slice them, you have kappa by 2 bit slices. Now, can I just use these kappa by 2 bit slices and run the half-gate scheme twice to get these kappa bits garbled gate and then retrieve the entire label in the end? If we see, it's still 2 kappa bits because you need 2 kappa bits for a kappa bit slice, which means you need kappa for each of these instantiations, which would mean that I will still have to send 2 kappa bits of size garbled gate. But very shortly, what they try to do is they sort of see that there is the ciphertext, but if you can somehow garble it in a way where you sort of happen to share one ciphertext in both these, then you don't have to send it both the times. You just send it once, and then that would be an optimization in a sense of you're saving kappa by 2 bits per gate. Right. So the idea here is now that can we use all these techniques to just extend and see if we can garble higher input gadgets? If so, which if there are any in the first place that we can use these techniques for? So we actually answer this question in the negative. So let's just go back to what gadgets mean here. I'm just giving an example of a 3-input gadget here. It might mean something like a 4 or 5-input gadget. And in this case, we just had the same garbled gate here. Instead, we have some sort of gadget which takes in multiple inputs and then takes, and you obtain the output of a function with more than 2 inputs. Right. And now we want to sort of go back to the half-gates equation, because that is where the core of the impossibility lies. And we want to see why we cannot do this. So I'll go through a few steps that sort of rewrites this equation in terms of linear variables in linear equations in x, y, and z, which are the inputs. in this case, X and Y actually. And then I guess it becomes a bit more understandable. So if you see here, we are actually including this delta, and we are including C0 everywhere. This just means that I'm encrypting the label C0 when I had to give out C0, and I'm encrypting the label C1, which means that I include the delta additionally in this equation, so that you're actually encrypting C1 in that case. This can be rewritten to this equation there inside the matrix, because then it means that it sort of denotes which label is being encrypted in each equation. And further, we want to rewrite all the other parts of the equation also in terms of X and Y now. Let's consider this truth table. It might seem random, but we will sort of see why this is important. If you consider this truth table, you can see I just want you to observe the column here, which is 1 XOR X. This is the output column for 1 XOR X. And now if we go back to the equation, you will see that there is something happening with the hash matrices here. The hash matrices actually can be rewritten in terms of X and Y. And it inherently comes due to how we actually use these hashes in every equation. So we simplified this M, where we replaced all these columns with certain variables because of the way we use these hashes. Similarly, we can do the same with the gate matrix V there. And in the end, if you remember, the addition of A0 and A1 was actually subject to the evaluator having access to that particular label in any row. If it does not have access to that label, then you cannot add it, because then you may not be able to sort of make the evaluator evaluate that equation again. And this sort of constraint can be captured by rewriting this control matrix. This is the addition of extra labels by just including the active label, as we call it, in a sense that the active label is the one that the evaluator holds, which can be rewritten as A0 plus X delta and B0 plus Y delta here. Yeah. So now we just have a more cleaner structure that we can sort of study, where we have everything rewritten in terms of X and Y. And one major observation we can make here is that all these three matrices should share the same column space, or at least in this case, actually, R of X comma Y can be a subspace of M of X comma Y, so the column space of MXY. But in the end, they should have some commonness in the column space. And that is where, just going back as to why I just want to discuss why the source of linearity is present in this set of equations. So we queried h of B0. You cannot use h of B0 if the evaluator has h of B1 in a particular row. Similarly, if you can have any linear combination of A0 and B0 that you're querying to the hash. If you're using it, you can only use it at a place where it's it can be queried by the evaluator also. And this constraint, along with the free XOR constraint, sort of makes it a case that anything in the column of matrix M is always a linear function of X and Y. As long as you're restricted to like making linear queries to the hash, which is actually observed as something that helps the optimization in 3/2, and it sort of does not help in the higher input case. This is the observation. So even here, you can extend this entire set of equations in some sense to also garble higher input gadgets. You just have to include more hashes, which also queries the third input, etc. And you will have to replace the output label here with just not X and Y, but rather it's just the function of the function that you wish to compute. And even here, this linearity comes up. It's nothing different, because even if you go to the higher input case, If you're still making linear queries, it will be linear in the inputs. It might not just be X and Y. Now there's also Z. Here it's I, J, and K. I'm sorry. Right. The thing is, if we observe, we know that Vxy, Mxy, and Rxy, all of them are at most linear in X, Y, and Z. Right? If I now choose to include this label on the left-hand side, which is C0 plus Gxyz, and this function is not linear, right? Let's say it's a 3-degree function. Then you will automatically have a 3-degree term on the left-hand side of the equation for which there is no 3-degree term on the right-hand side of the equation, because this side of the equation can at most have linear times linear, which is a quadratic equation. Or linear in X and Y. What does this mean? That means that the term corresponding to the 3-degree term here, which is delta, that has to be 0, which is sort of an impossibility because you do not want your 0 label and 1 label to be the same label. And this does not help in the slice setting because, as I said, what you do in the slice setting is you sort of apply this on multiple slices, but then the structure of the equation does not change. It remains the same. So any inherent limitation like this that applies to the half-gate scheme will also apply to the sliced version. So it sort of shows that a framework that you extend this way does not actually give you, that does not enable you to garble gadgets of degree greater than or equal to 3. So this is the first result we have, and an orthogonal result to this is something which we define as oblivious garbling, just to show that maybe we should consider garbling gadgets directly. And for this case, it sort of achieves gate hiding, right? But just to stress that this scheme also works with the current schemes, it will achieve the same communication complexity as what is there now. But I'll get back to it. So the idea of gate hiding in garbled circuits is essentially to introduce this notion of gate or circuit privacy from the evaluator. In traditional settings, because the garbler is just encrypting this truth table, it can also hide what the truth table is and then send it to the evaluator. And the only thing the evaluator needs to know is which row to decrypt. However, there is no notion that defines this in terms of the garbler, right? So we sort of show how to achieve gate hiding from the party that is actually garbling the circuit. This will require a slight change in the definition of garbling schemes because it's inherent in the BHR scheme, BHR definition, that the garble takes in the function as input. The garbler takes in function as input. So what we do is we instead just give the topology, and so this means that our scheme also needs to leak topology here. But once we leak topology, then we can achieve oblivious garbling, which we define to sort of capture this gate hiding notion from the garbler. The idea is essentially to consider this particular gadget, which is X and Y, X or Z. If you look closely, this sort of has an AND gate in it and an XOR gate in it. So if we somehow can let the evaluator program this gadget, program the inputs of this gadget, then the evaluator can choose if it wants to evaluate this in as an XOR gate or as an AND gate. The idea is to replace all the XOR gates and AND gates in any circuit with this particular gadget, and then let the evaluator program these inputs. If you want to program it as an XOR gate, then you program the X value to 0, and if you want to program it into an AND gate, then you program the Z value into 1. So there is a problem. The problem is it has to do everything while keeping this oblivious to the garbler, because the garbler cannot know if it is the X value that is being programmed or the Z value that is being programmed. And we know that the garbler knows the topology, which means this cannot be done during garbling. So what we do is, and it's easier for the input gates because the evaluator gets to run an OT for this and it can just program whatever it wants for the particular wires. But in the intermediate gates, it's not possible. So what we do is we just let the garbler garble every gadget independently, which means that it sort of produces these garbled, these output labels and a garbled gate for that independently. And now, to sort of let the evaluator be able to evaluate this, what we do is we use the soldering technique from the Lego paper that sort of lets you connect one wire dynamically to another during evaluation. How do they achieve this? Okay, this is the goal. The goal is essentially the evaluator has a wire XB, and what it wants to obtain is the same valued label on the wire Y. For this, you can just release X0 XOR Y0, and the free XOR sort of helps you transfer it in a sense that when you have XP, you can use this extra released value to sort of get the value for YB. Now, as we discussed, it can be soldered into an XOR gate or an AND gate, and for this we just let the evaluator run an OT for each gate to sort of let it decide on which one it needs to obtain, and once it's obtained, it can complete its garbled evaluation. Just to conclude, we showed that existing framework cannot be used to sort of garble higher degree gadgets. But orthogonally, it might still be interesting to look at other schemes that might do better in terms of garbling higher degree gadgets, because there are certain properties that we can achieve that is not so straightforward if we don't consider such gadgets. Thank you.